Welcome, it's 9 o'clock. Welcome everyone to the PyLith modeling tutorial in 2015. I'm Brad Aagaard. I'll be leading this tutorials this morning. Charles will lead the tutorial this afternoon. Matt Knepley will lead the tutorial tomorrow morning, and then I'll lead tomorrow's afternoon tutorial. So first of all, I'll go over sort of a very brief introduction to the entire tutorial, and then we'll jump right in and talk about PyLith, CUBIT / Trelis and Paraview, and we'll go through sort of an overview of PyLith and its features, followed by some hands-on examples. So this is the three of us. I am in Menlo Park, California, in the United States, at the Earthquake Science Center of the USGS. Charles Williams is at GNS Science in Lower Hutt, New Zealand, where it's currently 4 in the morning, so he's still asleep. Matt Knepley, I've listed University of Chicago. That should be Rice University. He is in Houston, Texas, and he's teaching this morning and this afternoon, and will join us tomorrow. Here's the overall view of the workshop with the 4 sessions today and tomorrow. We're hoping to have a gravity and finite strain session for this tutorial. We are still ironing out the final issues related to a good example of gravity, initial stresses, and finite strain. So rather than try and cram it in to this 4-session tutorial, we're going to add a bonus session, probably about a month from now. We'll find a time that fits our schedules. It'll have the similar sort of general time during the day, probably either 9 to 11 or 1 to 3 in the afternoon Pacific time. I've color-coded this these sessions. Most of them have a short presentation at the beginning, and then a lot of sort of hands-on showing you how we go through and do the various modeling and run the examples. So we'll run through the examples using PyLith version 2.1.0. We'll show the meshing. I use CUBIT. That's what I have access to. Charles uses Trelis, and so that's what he'll be showing. We'll be running PyLith, and then we'll do the visualization with Paraview. For those of you who may not be familiar with Adobe Connect, for the audio input-output, your microphones are disabled by default. We found that this generally works best when we have so many people. And so you type your questions in the Q&A panels and in the comments in the chat window. If it becomes necessary, we can enable your microphone. But in most cases, we find it's a lot easier with so many people to maintain the good audio quality, reduce the bandwidth, to have just one microphone enabled at a time. The Q&A pod, as I mentioned a few minutes ago, that's where we would prefer you submit your questions. It allows Adobe Connect to track which ones have not been answered, and we can archive all the questions and the answers. The chat pod is great if you're having sort of for logistical issues and questions that may need immediate feedback. So if I asked some sort of question about can you hear me, when I asked that several minutes ago, everyone typed in yes, so that was a good indication, and that was great for people to use the chat window for that. In general, we've had good experiences with Adobe Connect, but occasionally we do run into minor technical issues. Usually it's with audio due to variations in available bandwidth. The instructors, all 3 of us, will be using good internet connections, and so we don't anticipate any problems. If we do find problems, please be sure to chime up in the chat window, and we'll do our best to remedy those issues as quickly as possible. Getting help, the best solution for help is to read the PyLith manual. It's right around 200 pages. There's a lot of examples in there. We're always looking at ways to improve it. So if you can't find something in the PyLith manual and you find something confusing, please let us know. It's best to try and work through the problem on your own. You'll learn more the deeper you try and dig into the problem and sort of try various things. Submit your questions to cig-short@geodynamics.org. I gave the link to the CIG short mailing list and all of the CIG mailing lists. It's best to just subscribe to that list. Around these tutorials, there's a little more traffic, but generally you're not going to get inundated with a bunch of messages every day. When you submit a question, please describe the problem as best you can. And if there is an error message, send the complete error message. It's better to include more than include less. Include the platform you are using, the PyLith version, or whether it's the binary package or you built PyLith from source. We will try to respond as best we can during the tutorial. If it's a very detailed response required, we may sort of defer it during this tutorial to the next session. So particularly if we want to show an example of how to do something and someone asks that in between sessions, we'll defer that to the next session. And if you have questions, it's great to subscribe to CIG-short@geodynamics.org. We find that it's very beneficial for when people submit questions. Other people often have the same questions, so you get the answers when someone else asks a question by subscribing. And we also ask for community feedback using the CIG short email list. So some of you may not be familiar with CIG. CIG stands for Computational Infrastructure for Geodynamics. The website is geodynamics.org. The objective of CIG is to develop, support, and disseminate software for the geodynamics community. It is a coordinated effort to develop reusable, well-documented, open-source geodynamic software. It forms strategic partnerships with the larger world of computational science and geoinformatics, and provides specialized training, such as this one, for using this software and other workshops related to training and interaction with the larger earth science community. The underlying principle behind CIG is that earth scientists need help from computational scientists to develop state-of-the-art modeling codes. For PyLith, Charles and I are the earth scientists, and Matt Knepley is a computational scientist, and we have found this collaboration to be very beneficial in terms of the quality of code and the sort of sophistication and maintenance and testing that we are able to do with PyLith. CIG is an institutional-based organization. It's very open. Any institution seeking to collaborate on the development of open source geodynamic software can participate. There are no cost or size requirements. Some institutions have multiple people participating, some only have one. We're currently around 50 member institutions with 10 foreign affiliates. The second round of NSF funding ended sort of theoretically in July. There was sort of enough leftover money that there's current funds through the end of this calendar year. And a proposal was submitted at the beginning of July for another 5 years of continued funding through mid-2020. There are multiple working groups within CIG. They're organized by subdisciplines. They're part of the short-term Tectonics or short-term Crustal dynamics working group. There is a longer-term Tectonics working group related more to erosion and processes occurring on the 100,000 to 1,000,000 year time scale. We're primarily concerned with earthquake, volcanic deformation that's on the order of seconds to thousands of year time scale. There's a working group for mantle convection, computational seismology, geodynamo, and magma dynamics. For the short-term working group, our spatial scales on the order of about 1 meter to 1,000 kilometers, temporal scales from less than a second to about 10,000 years. This working group was originally formed by Brad Hager and Mark Simons before CIG was funded, way back in about 2003 to 2005. There was a strong connection to the Southern California Earthquake Stress and Deformation over Time Focus Group, and builds connections with other Southern California Earthquake Center working groups as well. And the SCEC also participates and helps fund some of our workshops. CIG has staff in UC Davis. That's where it's headquartered. That's where Louise Kellogg, the director, is stationed. She's a faculty member there. The director handles the day-to-day decisions. There's a deputy director, Helene Huang. They often participate in the workshops. There is a science steering committee that is made up of members of the community. It is the voice of the geophysics community and helps prioritize the competing needs of all the various disciplines to decide what software should be developed. There is the executive committee that is the primary decision-making body that handles all the approval of the contracts and other contractual arrangements. The member institution representatives vote on membership applications and bylaws. There are also the various working groups that are now having a more formal role in supplying information to the Science Steering Committee and deciding what should be developed. Community members collaborate with the CIG staff to develop software. Almost no CIG software is developed exclusively by CIG staff. The model that's being used now is almost exclusively members of the community that supply the scientific background, and CIG will supply computational science background either through staff members themselves or other members of the community. Software development is the primary activity of CIG. The next is probably the workshops that are organized by one of the more working groups. And they also hold some additional workshops that focus on more general topics that apply to multiple working groups. There is training in the use of CIG software, such as this one. It really is a virtual community, so the geodynamics.org website is used to distribute the software, the documentation, manage the mailing lists. There are also wiki-like web pages that help the community get involved. Here are covers from various CIG software. The pictures are a little old, but all of this software is currently, well, almost all of it is being maintained. You'll notice that there's a wide variety of tools and a growing list of tools. CIG manages the development of a number of packages, but it also archives additional packages from the community. They are generally not supported, but usually there's a tarball that's available from the CIG website. If you go to the CIG website, click on software, you can see the list and the status of each of the software packages. For short-term crustal deformation, there are primarily 3 packages that related to CIG. There's Relax, which is developed by Sylvain Barbeau, who is now at the Earth Observatory of Singapore. It solves 3D problems associated with earthquake faulting and quasi-static viscoelastic deformation. It generally applies to a homogeneous half space where the geometry does not change significantly. In this tutorial, we'll cover PyLith, which solves 2D and 3D problems and can handle both quasi-static and dynamic viscoelastic deformation, as well as elastoplastic deformation, a variety of different geometries in terms of you can make your fault surfaces as complex as you want. You can make your material properties in terms of their spatial variation as complex as you want. The methodologies start to break down where the geometry starts to change significantly, and that's where people, if they're looking at longer term deformation, use Gale. There's also some additional software used in the community These are for solving problems of orogenesis, rifting, subduction, and including free surfaces that are coupled to surface erosion models, where you have very large deformation strains, sometimes much greater than 1. So that's it for an overview of the tutorial and CIG.